as part of ITCS, where it features junior researchers who are close to graduating on either end, either graduated a few years ago or are graduating soon or are graduating this year. So we're lucky today to have an exciting lineup of 14 young researchers who are going to sort of tell a little bit about themselves. I've really put little to no restriction on what they must say or do. So we'll see what they have and how they choose to present themselves. We're going to start in about 30 seconds. Yeah, and in fact, our first presenter is going to be Pratik Soni. Pratik is at Carnegie Mellon, and yeah, he'll be our first presenter, and we'll take it from there. You can feel free to start in. We're going to be on a very tight schedule. You can start in 3, 2, 1. Take it away.
Hi, everyone. My name is Pratik. I'm currently a postdoc at Carnegie Mellon University, and I'm looking for tenure track positions in theory and cybersecurity this year. My main research is in cryptography. So cryptography is everywhere today. It's used every time your phone connects to the internet and anytime you use a credit card. And in fact, it's now becoming an integral part to more advanced and complex computing technologies like cloud computing, secure messaging, and blockchains. So let's look at the example of blockchains, right? Abstractly, it's a distributed ledger where users are allowed to post data and miners are responsible for maintaining the ledger according to some predefined rules. And blockchain needs a lot of advanced cryptography. In fact, blockchains have been a driver for a good fraction of recent innovations in cryptography. Despite this, one of the major challenges we face today in blockchains is that of scalability. An integral component of current blockchain systems are proofs. And here, prover overheads are becoming a major bottleneck and a primary challenge to address scalability issues. There has been some exciting work on optimizing time overheads of the prover, but provers' memory overheads have been largely ignored. And my work identifies this and gives zero-knowledge proofs where provers' memory and time overheads are minimal. As excessive memory usage inherently contributes more to time, we believe our result, which focuses on memory consumption, provides an approach to obtain better scalability. Blockchains are often viewed as consumers of cryptography, and this is the view I presented in the previous slide as well. But recently, I've been looking into blockchains as an enabler for doing cryptography. And in fact, you can do a lot of new cryptography using blockchains. And to listen to more about this, you should come to session number 15 at ITCS tomorrow, where we use blockchains to give new cryptography. Beyond connections with blockchains, I've also worked on building crypto systems that are secure against stronger attacks. For example, man-in-the-middle attacks are notorious and extremely difficult to handle in numerous cryptographic settings. My work here builds protocols that are resilient to such attacks. Another example here is of block ciphers, which are pervasively deployed cryptographic algorithms in practice. Here, my work tries to understand, formalizes security for blockchains in stronger settings where the adversary knows the underlying key. So beyond this, I want to conclude with a couple of future works that I'm very excited about. So note that the recent importance of zero-knowledge proofs makes it important to solve prover overheads, right? So one approach here is to whether we can use the power of parallel computing in order to improve the prover overheads. Secondly, I want to explore new connections between cryptography and blockchains. For example, there are new cryptography for blockchain applications like adapter signatures and contingency proofs. What's the next one? Similarly, there are numerous properties of blockchains that enable cryptography, one of which I presented to you in the previous slide. What is a new one that we could try to explore and get better cryptography? That's my time. Thank you. Back to the host.
Yeah, thanks. You're actually a minute fast in the sense that it's 3 minutes. You had 4, but if there's anything else you want to say, go for it. Or if there's any questions.
Yeah, I mean, I think I said as much as I wanted to say.
Cool, very efficient. In that case, we can get set up early for the next participant. Next up is Kiran Vadrahali at Columbia. So feel free to share whenever. Cool, and yeah, feel free to start whenever you want.
Okay, am I unmuted? Oh, good, okay. Yeah, hi, I'm Kiran Vadrahali. I'm a final year PhD candidate at Columbia, and I'm advised by Alex Andoni and Daniel Su, and I work on the theory and practice of machine learning. I'm currently looking for either industry research positions or postdoctoral positions. So let me tell you a bit more about my research. So there's two kind of main directions I work on. One is resource efficient learning, where I'm concerned about sample and time complexity of various kinds of models, in particular sparse models, low rank models, and I'm also working on streaming settings a bit more recently. And the second direction I call controllable and interpretable agents. So one thing will be something I call platform design, which I'll talk a bit about more later, online and reinforcement learning, and algorithmic game theory. And I'll give a little vignette of one of my works from each of these areas. And in future work, I'm interested kind of in directions in both of these areas. Okay. And I've also worked on many applications, and I continue to be interested in applications. So first, I'll talk about resource efficient machine learning. So one challenge in modern ML is that we deal with very, very large models like these giant deep neural networks. So one approach that we can go for mitigating the sample and time complexity is to look at low rank models where we replace the parameter matrices with low rank approximations. Okay. So I have a recent work with many people from Google, which is in submission and will be on arXiv very soon. And here we work on learning low rank deep models by replacing full rank layers with low rank parameters. And one question that's of importance is how do you initialize? And the standard way of doing it is to just use the SVD of some full rank initialization of the weights. We present nonlinear kernel projection, or NKP, which is essentially replacing the minimization of the Frobenius distance with the minimization of some kernel distance, which takes the nonlinearity in the layers into account. And we demonstrate empirical gains over the SVD. We also give a provably efficient optimal algorithm for the NKP. In the setting where we're solving it as a learning problem, we give an efficient learning algorithm. And we demonstrate both theoretically and practically that our method outperforms the SVD initialization, and especially along the axes of larger width networks and for lower rank approximations. So second, I'm going to talk about platform design, which is joint work with Christos Papadimitriou and Mihalis Yannakakis. So here we're dealing with the economics of the online firm. So online firm is a company like Google, Facebook, etc. And they want to create services which bring users convenience and knowledge, but also so that the users give them data. So users don't pay directly with money, they pay with data. And we want to understand how the online firm can go about designing such platforms. Okay. So we could start with a simple model where the agent lives in some Markov chain called life, and they go between the various states, and the online firm has to decide what platforms to build to get the agent to give them their data. So they can create a platform like, say, Google Maps. And then the agent can opt into Maps, change the transitions of their Markov chain, presumably for the better, while simultaneously giving up, say, their location data. So this problem is modeled as a Stackelberg game where the designer moves first and gives platforms to the agent. The agent now faces a Markov decision process, an MDP, and plays optimal behavior. And so we model this as a bi-level MDP optimization problem. And we study the computational complexity of this problem. And in general, it's NP hard when platforms are viewed as complements, but it's efficient to approximate in a special case when you view the platforms as substitute goods. And there's many directions for future
work.
Work.
Thanks, Kieran. Your time's up. If you could stop sharing. And Talia Eden is next at MIT. Talia, please feel free to share whenever.
Okay, sorry.
Cool. And take it away.
Okay, hi. Oh, sorry. Hi, my name is Talia Eden. I'm a postdoc at MIT and at Boston University, and I'm looking for tenure track positions in theory and graph algorithms. And my study is about sublinear time algorithms, where what we do is we assume that in sublinear time, we assume that the algorithm is not allowed to go over the entire input, rather just sample it in as few as possible locations, because maybe the input is too large. And the goal is to get a close to accurate answer. So what we do is we trade accuracy for efficiency. It means that we assume that the graph is too large to be stored locally, so it sits somewhere remotely, and we can only access it through queries and answers. And the goal is to minimize the number of queries to the object, to the graph, and the running time. And in this setting, I study motive analysis, where graph motives are small subgraphs that recur throughout the network. For example, this could be small stars or clicks, or even arbitrary subgraphs. And by looking at the statistics of these small subgraphs, we can gain information about the local structure of the graph. So for example, if we're looking at clicks, we can learn about the community structure of the graph, or learning about the star distribution, we can learn about the degrees distribution. So really, motive gives us information about the global structure, even though they are localized structures. More generally, for more concrete examples, in social networks, we can learn about missing friendships, in chemistry, imported molecules, maybe missing roots in maps, and also in biology, we can see that this is a folding network, and we can see that clicks correspond to folding sites. So really, by learning about motives, we can learn about the structure of the graph, and this is the motivation for my study. So in this setting, I studied a lot of motives, and when I started my PhD, what was known is how to approximately count edges and stars in a graph, in general graphs. So we first extended these results to approximately counting triangles and click, and then we also considered these results in bounded arboricity graphs, which are graphs that have more structure, and gave improved results for these types of questions. And one notion that came up a lot in this work is the notion of uniform sampling, of counting via uniform sampling. So we also initiated the study of uniform sampling in general graphs, gave results for uniform sampling of edges in sublinear time. These are the first results of this sort. And we also extended it again to triangles and clicks. And then we also gave results for sampling multiple clicks, which were later shown to be optimal by Tatek and Thorpe. So this is the type of work I've been doing. And also, sometimes when you go from theoretical results to practice, some new consideration arise. For example, you don't control the query model, or you want to use more structure on the graph to get improved results for real-world graphs. So I also do practical algorithms, meaning algorithms for real-world networks. So kind of to summarize my interests, I did a lot of work on sublinear time motive counting, initiated the study of sublinear time motive sampling, and also I have worked in other computational models and other types of questions. So these are kind of the set of results I had for sublinear motive counting. This is for sampling, and for a subset of this result, I won the 2020 Best Dissertation Award. And also in other models, I first studied these types of questions in other models of computation, as the massively parallel computation, distributed algorithms, congest, and learning assistant, and also studied other results, other questions like graph property testing of graphs and Boolean functions.
All right, thank you, Talia. Your time is up. Next up is Jihan. Please screen share whenever you're ready. And Jihan is at the University of Chicago.
Does that work? Yeah, can you see me?
Go ahead. Yes.
Okay.
Go ahead.
Okay. So hello everyone. I'm Jihan Tan. I'm a 6-year PhD student at University of Chicago. So I'm graduating this year, and only applying for postdocs. And my advisor is Julia Chuchoy from TTI. So so my research mainly focused on graphs. So I did research on all kinds of graph algorithms. And most of my time was spent on classical graph algorithm in the past 5 years. So for the classical graph algorithms, it is not the vertex cover type, it's not the minimum independent set type, but the highlights, the keywords that I want to highlight are crossing number, exclude degree theorem, and flow cut and distance falsifiers. So it is really the structural type of the graph algorithms that I work on. Okay, and in the past 1.5 years, I'm also switching to graph algorithms on this new computation models, like the distributed model, dynamic model, and the sublinear model, and also working on graph algorithm in this new computational models. And I'm also interested in graph, in the intersection between the graph algorithms and other related fields. Okay, so basically one word, if you want to remember me, it is graphs. Okay, so I would like to highlight one result, actually a sequence of 2 papers on crossing number. Okay, so what is a crossing number problem? The input is just a graph, and the output is a drawing of the graph in the plane. Okay, and the drawing is a mapping that maps the vertices into points and map edges into curves connecting the endpoints. So for example, if your input graph is K5, a click on 5 graph on 5 vertices, then this is a drawing of K5 into the plane. And this drawing have only one crossing. So this is an intersection between these two curves. And we know that K5 is not a planar graph. So the crossing number of a graph is defined to be the minimum crossing number of any minimum number of crossings in any drawing of the graph. So the crossing number of K5 is 1. So what is known about this problem? So it has a very long history. It was proposed by Turan in 1944. And by the time of 2014, already 700 papers have been written on it. And in general case, we basically know nothing. The strongest hardness result is APX hard, and there's no non-trivial approximation. And we do have one beautiful result about this crossing number, which is this crossing number inequality. It basically says that if the graph is moderately dense, then the crossing number has to be very high. And the most interesting part of this problem is really when the crossing number is small, but whether or not you can find a good drawing with small number of crossings. So it's reasonable to look at the boundary degree graph, which is indeed the main research direction in the past 10 years. And the strongest negative result in this case is still only APX hard. And the approximation algorithm is improved from the O tilde n approximation like more than 10 years ago to n to the 0.9 10 years ago, and recently to square root of n like 3 years ago. And our result is that we obtain a n to the little 1 approximation to the crossing number on boundary degree graphs. So this significantly improved the previous approximation and this first subpolynomial approximation algorithm for this problem. Okay, that's all I want to say. And graphs, my research is on graphs. Thank you.
Cool, thanks. You have another 20 seconds roughly if you want, but
oh, yeah, okay, I can give
okay,
the rest
cool.
of the time.
Yeah, thanks, Jihan. Next up is Ian Mertz. Ian is at the University of Toronto.
Can you hear me?
Yeah, we can hear you great.
All right, perfect. So hi, thanks for coming. My name's Ian. The things I think about nowadays are composition theorems and getting postdocs. So hopefully you'll think about them too after this. So just quickly, a composition theorem is the following. You have two functions that you care about, f and g, and you have some way of composing them or combining them into some superfunction. And the question is it easier to solve the superfunction than to solve the two individual functions by themselves? So in terms of combining, there's two ways that that most people usually think about, call them sequential and parallel. So in the sequential way, this one over here, you take a copy of f and you replace each of its variables with a copy of g on some fresh set of variables. Sequential because it seems like you have to solve g to solve f. And then in the parallel world, you just have f and g on some separate set of variables, and you want to solve both of them and output their answers. So you can't cheat your way out of solving g. You actually have to output both answers. But if you do some pre-processing or alternate or something, maybe you can save some time or other resources. And in terms of resources, when you specify a composition theorem, you also have to talk about what you're trying to save. And the ones that I think about are formula depth, and Turing machine space. So you've got a space-bounded Turing machine. So you can take any combination of these or anything else you want. The two that I care most about are, so the first one is you take the sequential method of composing and you look at formula depth. And this is connected to questions about polynomial time versus formula size, NC1. And here the answer should be that no, you can't save anything. Your depth of your composed function should be roughly the sum of your depths of the other two. At least that's what I think, and that's what I've been working on. So there's lots of applications to, formula size is a major open problem by itself, but there's also connections to like meta complexity, especially in proof complexity. And if you come to my talk on Thursday, you can see some new connections between these lifting theorems, as they're called, and the sunflower lemma. So there's some connections to combinatorics that run pretty deep. And the other setting I care about is you take the parallel method and you ask the question for space. And here I actually think the answer should be, yeah, you can save quite a bit. So this has a lot of applications in just classical space-bounded complexity. We recently showed, and this is online. You can we recently showed that you can get better algorithms for this problem called tree evaluation, which we suspected would be able to separate log space from P. Turns out there's some pretty good space algorithms, and they're only getting better. So there's classical space. There's this mode called catalytic space, which I think is super cool about borrowing memory. And we have some work coming out pretty soon about amortized space. So I think that these composition theorems are very interesting, and I hope that you will grow to think about them. And if you're too busy to think about them, then consider hiring an expert like me. That's it. Thanks.
Perfect. Thanks, Ian. You're actually ahead of time. In which case we can go ahead with the next speaker, who is Pedro Paredes. Pedro is at Carnegie Mellon, and you can feel free to start whenever you're ready.
All right. Can you hear me?
Yeah, I can hear you great.
All right. Hello, everyone. My name is Pedro Paredes. I am a fifth-year PhD student at Carnegie Mellon, and I'm advised by Professor Ryan O'Donnell, and I'm currently looking for postdoc positions or equivalent positions. Okay, so a summary of my research interests. My research focuses mainly on spectral graph theory, pseudo-randomness, and coding theory. Concretely, I work on graph expansion, properties and applications, meaning I work on problems of the following nature. How can we build graphs or objects that are expanding? Or how can we analyze the expansion properties of graphs or objects that are drawn from random distributions of different natures, and also how to apply these things to different areas. And this ends up having applications in so many areas of theory, including, like I mentioned, coding theory and pseudo-randomness, and also spectral graph theory. More broadly, I'm also interested in sort of other aspects of theory, like complexity theory, combinatorics, and random matrix theory. These end up being related to the things that I already work on, but I'm also interested in these questions in a more broad sense. Some of the work that I'm currently doing and I'm planning on doing is on high-dimensional expanders, where my goal is to sort of extend some of the ideas and some of the things that I've worked on for graph expansion for these high-dimensional objects that have been very popular in the theory community lately, and they've led to so many new results in different areas. And I'm mainly interested in problems related to construction of these high-dimensional expanders, but also in problems that related to random high-dimensional expanders, or how to provide, for example, a distribution of high-dimensional objects, simplicial complexes that have properties of high-dimensional expansion. I'm also interested in spectral algorithms, for example, problems related to sparsification of graphs or sparsification of hypergraphs. And this is something else that I have been thinking about, as well as some other problems related to the previous things that I've mentioned, like graph expansion. I also wanted to mention that I'm also interested and experienced in teaching, but I'm mainly doing research. Okay, I wanted to sort of give you very briefly some a selection of some of my results that I've worked on so far. One of them is this result on explicit near-Ramanujan graphs, where we showed how to construct these near-Ramanujan graphs, which are near-optimal spectral expanders. This is joint work with Siddhant Mohanty, who was a PhD student at Berkeley, and my advisor, Ryan O'Donnell. And this work, we extended some tools that already sort of existed in this area, and we had to deal with problems related to probability theory, to combinatorics, and so on, to sort of build this framework to build graphs that are expanding using lifting theorems. So this was one of the results that I worked on recently. We then sort of expanded on this result, and we have this new result that is set to be published at ITCS this year, which are on explicit abelian lifts. This is sort of a generalization of the result from the paper that I just mentioned, where we showed that these objects these products called abelian lifts, when we do it at random, they preserve spectral expansion. And the main reason why we wanted to do this is because we could use this to apply this in different areas, mainly in the construction of different types of LDPC codes. And this led to good quasi-cyclic LDPC codes, which are a family of error correcting codes that are actually used in practice. And are really popular nowadays, but also a family of quantum LDPC codes. This work has been recently subsumed by this work on asymptotically optimal LDPC codes, but our work showed sort of like a subset of that result, I guess. by expanding some of these, by showing these properties about abelian ellipse. So this is joint work with Fernando Geronimo, Grania Geronimo, Tushant Mittal, Ryan O'Donnell, and Madhu Trusiani. Okay, and that's it.
Cool.
Thank you very
Thanks.
much.
Perfect timing, Pedro. I was just going to cut you off. Okay, next up is Alex Block at Purdue. Alex, feel free to share and take it away whenever you are ready.
Oh, sorry, give me 1 second.
Yep.
I'll be quick, so that's okay. Let me share screen. Okay,
Cool.
Can you
Yep.
see the slides?
It seems to be a bunch of diagonal lines. I can't see anything.
Okay. Okay. Do you want to skip me? I think.
Yeah,
it's
Anish, you want to go next? Anish, are you there?
Sure.
Sure. Go ahead. We've got a little bit of a leeway, so it's okay. We can handle this.
Right.
But yeah, go ahead.
I don't have that much to say. I'm Anish. I'm from Carnegie Mellon. I'm co-advised by Pravesh Kothari and David Woodruff. If you take them, you'll get me. Hopefully, this will be our genealogy tree in a few months. I'm a fifth-year PhD student, and I'm looking for a postdoc. My research interests are essentially the union of the research interests of David and Pravesh, but in particular, robust algorithm design, the sum of squares hierarchy, and numerical linear algebra. I'm also mainly interested in algorithmic problems that show up in any TCS domain, and if it has an interesting flavor, I'd be happy to think about it. Okay, so let me say a bit about robust statistical models, which has been a main theme in my PhD thesis so far. So here, instead of just given IID samples from a distribution, you're given IID samples, but then some fraction of the samples are corrupted by an adversary. And this model was initially studied by Tukey and Huber back in the 60s in the statistics community, and it's used to capture systematic outliers and error. And there's been decades of work on designing statistical estimators that are robust in such a sense, but these are typically not efficiently computable in high dimensions. And there really has been a lot of work. There are like multiple textbooks on designing such estimators, but most of my work focuses on estimators that are efficient in high dimensions. So let me give some examples of how to fit models to data when the underlying data is corrupted in this malicious model that I just defined. Some examples of these include learning mixtures of arbitrary Gaussians, clustering the non-spherical mixtures beyond just Gaussian distributions, regression, and list decodable subspace recovery and regression, where here, instead of just a small fraction of your data being corrupted, potentially, majority of your data is corrupted, and your goal is to output a small list. Another example is like fitting a dual layer neural network, which doesn't exactly work in this model, but it has other robustness guarantees. Okay, and the other theme in my research has been designing algorithms for numerical linear algebra. Here, the focus is slightly different. We want to design like really efficient algorithms for things like dimensionality reduction, where you, in fact, don't even read most of the data. So these are like sublinear algorithms. And some examples of these include algorithms for low rank approximation when you're promised that the input matrix is positive semi-definite. Here, you don't even read most of the matrix and can output a low rank approximation. A similar result for distance matrices. Another problem that I really like is to test whether a matrix is positive semi-definite without reading most of the entries of the matrix. So this work addresses this problem. Then I've looked at generalizations of low rank approximation and PCA to other unitarily invariant norms, not just Frobenius and operator norm, but an arbitrary Shadden B norm. As well as designing algorithms which again don't read the entire matrix but work for kernel matrices, which again have structure. So the overall theme here is like, if your underlying matrix has structure, can you exploit it without reading all of the matrix and come up with hyper efficient algorithms? Okay, that's all I have. I don't need the rest of the thing. Thanks.
Perfect. Thanks a lot, Anish. Yeah, that was great. Thanks for picking up real quick. Next up is Ariel Schwartzman. So feel free to share whenever you're ready. Ariel is at Dymax.
Hi, can you see my screen?
See you. We can't see your screen shared. Feel free to share.
Sorry, it seems I'm also having some issues.
Yep. if you want, we can put you at the end as well. If
Yeah, that'd be good.
okay, Sayit, are you there and ready?
Yes, I'm here. Let me.
Cool. All right, let's go with Sayit, who is Sayit Sharifi Malvajerdi, who's at University of Pennsylvania. Take it away.
Can you see my screen now?
Yeah, it looks great.
Okay. So I'm Sayit. I'm a PhD student in the statistics department of the University of Pennsylvania, where I'm advised by Michael Kearns and Aaron Roth, and I am on the market for faculty positions. My research is on enforcing ethical and societal constraints in algorithm development. And so far, I have mainly focused on 3 topics under this umbrella of ethical algorithm design. These topics are algorithmic fairness in machine learning, privacy preserving data analysis, and the last one is machine unlearning or data deletion, which I'm going to tell you briefly about today. So machine unlearning is basically motivated by the right to be forgotten of GDPR, which says that if you're a user of a company, say Facebook, and if at any time for any reason you want your data to be deleted from Facebook, you can have that request and Facebook must immediately delete your data. But it is easy to delete data from databases, but the more important question here is that how do we remove the influence of these data points from the models that have used those data in the training procedure? And when you think about this problem, the very first solution that comes to mind is that we can remove these data points from our databases and we can retrain our models from scratch on these updated data sets. But as you can imagine, retraining from scratch can be computationally expensive. And this brings us to this question. Can we do better than retraining? Can we design a deletion or unlearning algorithm, which is much faster than the retraining procedure? And also the outputs of this unlearning algorithm are indistinguishable from the outputs that would have arisen from the retraining procedure. So in some sense, unlearning algorithms are supposed to mimic the retraining procedure for us, but hopefully with much less computational cost. So with that intuition in mind, let me move on to formalize a model and a definition for an unlearning algorithm. So suppose at training time, we have some data set D, training data set D, and we use some training algorithm A to train a collection of models. And let's call the algorithm that we will use to perform deletion for us by R sub A. So at deletion time, R sub A gets a deletion request. And also it gets any auxiliary information from previous round that can help facilitate the deletion procedure for us as input. And it outputs a new collection of models. And these deletion requests arrive sequentially over time. Now let's see what would happen if we wanted to retrain in every round. We would basically remove these data points from the original training data set, and we run the same training algorithm on these updated data sets. So for example, for the first deletion, we remove data point Z1 from the original training data set D, and then we run the same algorithm A on that data set. Now we have all the ingredients to formally define what we mean by an unlearning algorithm. We say that R sub A is an unlearning algorithm for A if the distribution of the models output by R sub A on the left-hand side is equal to the distribution of the models output by the retraining procedure on the right-hand side. So if R sub A is an unlearning algorithm for A, according to this definition, and if R sub A is faster than the retraining procedure, then we would strongly prefer to use R sub A instead of the retraining procedure. That's the high-level idea. And that was a brief introduction to machine learning. I've done a couple of works in this domain. In the first one, we focused on the convex empirical risk minimization setting, and we developed unlearning algorithms that only use gradient updates. And in the second one, we used techniques from differential privacy to design the first data deletion algorithms that, unlike some prior work, have rigorous guarantees against adaptively chosen deletion sequences. And these algorithms work in the most general non-convex settings. So here are my papers on machine learning, and feel free to reach out to me if you have any questions. Thank you very much.
Perfect. Thanks a lot, Sayit. Perfect timing, and thanks for picking up on short notice. Next up is Pranthar Ghosh, who's at Dartmouth College. Go ahead whenever you're ready. Pranthar?
Can you hear me?
Yeah, I can hear and see. Go ahead. Yep.
And you can see your share my screen?
Yeah, we can see your screen shared.
Yeah. Okay. Yeah. Hello?
Yeah, you're fine. Go ahead whenever.
Oh, okay. Okay, hi, I'm Prantar Ghosh from Dartmouth College. I'm a fifth year PhD student. I'm advised by Amit Chakravarti, and I expect to graduate in spring 2022. And I'm mostly looking for postdoc positions starting summer or fall 22. So my research area is in the data streaming setting. So here we receive an input as a sequence of elements A1 to AM, let's say, and we want to maintain a summary of the data and want to output a correct answer at the end of the stream to some problem. And our goal is to optimize the space usage. Now, my focus is on graph streaming. And here, a graph problem is what we focus on, and the graph is built by a sequence of edge insertions and deletions. And the problems we want to solve are something like, is the graph connected, or how many triangles are there in the graph, or let's say we want a proper coloring of the graph, and so on. I have also considered variants of the data streaming model, for example, adversarially robust streaming, where instead of fixing an input stream in advance, an adversary adaptively decides it. It sends us the stream element A1, receives an output to the current state O1, and decides the next stream element A2, this gets the next output O2, and so on and so forth. So then another variant that I have considered here is called annotated streaming setting. Here, it's an amalgamation of data streaming and a prover verifier system, where the prover knows the entire stream and it sends the answer to the problem along with a proof to the user, who acts as a verifier and wants to collect information from the data so as to just verify the answer and proof. And we would like to optimize the proof usage, the proof size, and the space usage in this setting. So now my research is basically on understanding the space complexities of various graph problems in this data stream setting and its variants, annotated streaming and robust streaming. And this involves designing space efficient algorithms and also proving the minimum space requirements or showing lower bounds. So let me briefly go over some of my contributions. So I have given the first foundational algorithms for some classical directed graph problems like topological sorting or feedback arc set. And I have also given graph coloring algorithms using very small number of colors, using a novel parameter called the degeneracy of the graph. I have designed annotated streaming protocols for certain graph problems, some of which were conjectured to be impossible, and some of which are optimal, probably optimal for those problems. I have also, and this in this ITCS, the paper we have, I have designed robust coloring algorithm, new techniques. And as part of lower bounds, I have shown limitation results of certain flavors. For example, for certain problems, I have shown that there is no sublinear space algorithm possible. For example, order delta coloring in robust streaming or kappa +1 coloring in standard streaming. I have shown that existing algorithms for certain problems are provably optimal. For example, topological sorting in tournaments. I have shown that natural generalizations of certain problems, for example, if we take coloring from standard to robust setting, or instead of delta +1, you consider kappa +1 coloring, where kappa is the degeneracy of the graph, then these problems become provably harder. And again, certain standard relaxations of problems, for example, considering random order streams instead of adversarial order, doesn't make this problem easier.
All right, thank you, Prantar. That's all the time we have. Next up is Yingkai Li. Yingkai is at Northwestern University. Feel free to screen share and take it away whenever you're ready.
Okay, thanks. Okay, hi everyone. My name is Yingkai Li from Northwestern University. I'm currently looking for both postdoc and tenure track positions. I'm going to talk about mechanism design with the endogenous information. And my research is in the intersection between computer science and economics. In the CS side, my focus is on the design of good algorithms in complex environments. Note that in many applications of interest, those algorithms are going to interact with strategic agents, and those agents can manipulate the input to the algorithms for the interests of their own. And moreover, those strategic agents often rely on their private information for making better decisions. And crucially, the information that the agent have as endogenous, meaning that what type of information the agent choose to acquire for making better decisions often depends on the choice of the algorithm. And my research is in this interdisciplinary area on designing good algorithms for systems with endogenous information. And in a sequence of papers, we are going to illustrate that this endogenous information is actually a crucial ingredient for designing good algorithms for various applications. This is illustrated by showing that actually many insights from the classical mechanism design, where we don't consider endogenous information, actually fail for those applications with endogenous information. And to resolve this issue, we are going to propose several novel ideas for designing good algorithms when there are endogenous information. To give you a more concrete idea, let's consider the following example of information acquisition. The classical work has focused on the characterization of scoring rules, which is essentially designing the reward functions of the agent to incentivize them to report their product information to the designer. An important ingredient missing from those previous work is endogenous information, means that those information is not endowed with the agent, and the agent needs to actually exert costly effort to acquire high quality information. And naturally, the designer would prefer the agent to exert the effort and report high quality information instead of doing no effort and to report some garbage information. And hence, the goal here is to design scoring rules that actually incentivize the agent to exert effort and then report the acquired information. And in our paper, we are able to show that when there are multiple tasks, an very intuitive approach is from the design without endogenous information is to score each task separately and elicit information from the agent separately from each task. And we are able to show that this design of separate scoring is actually pretty bad for incentivizing effort. And we are able to propose a very novel scoring rule that actually links the incentives across the different tasks and incentivizing the agents to exert effort on as many tasks as possible. And we are able to show that this is approximately optimal in any situations. And this example illustrates the importance of considering endogenous information for designing good algorithms. And finally, I would like to briefly talk about the other directions I'm also interested in. For example, I'm interested in designing simple mechanisms with practical implications that are approximately optimal and has robust performance guarantees in various applications. And I'm also interested in designing good learning algorithms in online environments with expanded feedbacks and a good mechanism for strategic agents have repeated interactions. And that's all. Thanks, everyone.
Perfect. Thank you, Yinkai. Perfect timing. Next up is Chris Jones at the University of Chicago. Take it away whenever you're ready, Chris.
Okay, thanks. Hi. My name is Chris Jones. Yeah, as mentioned, I'm at the University of Chicago. I'm advised by Aaron Putechin, and I'm looking for postdoc positions. So here I've shown some of the things that I like to think about. This is just a word cloud of terms that are related to my research. Yeah, if I had to summarize it, I'd say that I'm really interested in generic, powerful mathematical techniques and how they can be applied to computer science. So I really like math, but I like computer science more. So I just want to zoom in to a couple different regions of this picture and tell you about some of my research and why I'm interested in these areas and what are some future questions that we're considering. So the first area is kind of this central area, the sum of squares hierarchy. So sum of squares lower bounds is probably the most important thrust of my research in the recent few years. What is the sum of squares algorithm? It's this super powerful semi-definite programming algorithm. And it's been interesting because in the last couple of years, it's led to a lot of breakthrough algorithms, and in particular in two areas. The first one is in statistics, where we've got new algorithms for like tensor PCA and robust linear regression that really match predicted guarantees. And this paradigm has led to these breakthroughs. And the second is constraint satisfaction problems, where sum of squares is conjectured to be optimal under the unique games conjecture. And it's also led to a lot of interesting new algorithms for unique games, for example. So my work is mostly focused on lower bounds against this super powerful algorithm. So for example, we showed some lower bounds against some particular problems. And the technique we use to prove lower bounds is through combinatorial and spectral analysis of random matrices. And unfortunately, these are not really easy lower bounds to prove. Okay, so back to the word cloud, let's look at another area that I'm interested in, this upper left area, the combinatorics region. So through these papers on sum of squares lower bounds, we of course encounter some interesting combinatorics, mostly through this like matrix valued Fourier analysis technique. And I've also worked on some other related questions that came up. So here are two works of mine that are actually both appearing in this conference. So maybe you saw the talk I gave yesterday on the inner product polynomials, which is some really fun combinatorial stuff that we discovered. And then another paper that I've worked on is an approach to code upper bounds through semi-definite programs and linear programs. Okay, so that's that region. I just want to tell you about one more region, which is some new and exciting directions that I think are a field of future research, which is this lower right corner having to do with statistical physics and average case problems. So, okay, why do I find this very interesting? Because if you start to read the literature, you find that there's a lot of really incredible predictions and algorithms for these average case problems and for stuff like random CSPs. And yeah, one thing that we've been doing is proving lower bounds that match these predictions and trying to give algorithms. So I think there's a lot of opportunity to connect the insights from the different fields, both on a technical level and an intuitive level. So here's some future directions kind of studying this stuff. Yeah, I'll just put them here and maybe explain them really quickly. So some of this powerful technology in approximate message passing might have to do with other technology more in the familiar to computer scientists. Also interested in some walk-based rounding algorithms. And in general, can we understand the complexity of certification tasks, which is really what sum of squares is doing. So yeah, here's the word cloud again. Thanks for listening. Yeah, looking for postdoc positions. Thanks.
Perfect. Thanks a lot, Chris. Next up is David Weitz at Stanford. Please feel free to share screen and start whenever you're ready, David.
Right, so you see my screen?
Yes, yes.
All right, so as Gautam said, my name is David Weitz. If you want to think about how to pronounce that last name, think of the word invites and then drop the in. I'm a CMU alumni, alumnus. I am currently a postdoc at Stanford, and I'm looking for faculty positions. So broadly construed, I work on algorithms. Let's quickly revisit our classic view of algorithm design. So historically, the way we think about algorithms is you get an input, you spit out an output, and then you're done. Unfortunately, this view is becoming increasingly antiquated for a number of modern applications where really, you still have your input, but your output is very often externalized to users who in turn will keep generating more input to which you need to respond. So really what we have here is evolving inputs and evolving outputs. And if we want to think of some motivating applications where this is kind of the dynamics, the gig economy is a good place to look for this, where we have a lot of agents entering and leaving the platform over time. So for example, in ride sharing, we have drivers and passengers entering and leaving the platform. Same for food delivery, where food orders and food couriers arrive over time. So all these modern applications give a modern motivation to revisit the following key theoretical question, which is how should we react to evolving data? How should we maintain an evolving output in the face of evolving inputs? And there's various theoretical models that study this question. So we can ask, how should we react if we have to react immediately and irrevocably to the changes in the input? This is studied by online algorithms. We can also ask what should we do if we want to react quickly? This is the area of dynamic algorithms. And finally, we can ask how do we react if we have to react space efficiently, which is the area of streaming algorithms. So just to give you kind of a sampling of some of my work at the space, some questions I like to think of, does randomization help in the context of online matching and those general setting you can think of? And unfortunately here, the answer is no. Another type of question is, does randomization help in the face of adaptively changing inputs? And here you should be thinking about this feedback loop we had before. The algorithm externalizes an output to the users who, based on that, decide what changes to make to the input. And here there's a very strong positive result in a generic framework to design dynamic matching algorithms that work for adaptively changing inputs. Finally, in the context of streaming, we asked if the primal dual method is a useful tool for submodular maximization, and here too, the answer is yes. I guess we have another minute, so let me give you a bonus bit. I also have interests in distributed algorithms. So for example, we have this recent work on the first universally optimal congest algorithms for minimum spanning tree, min-cut, single source shortest path, and the like. Also have some interest in networking. For example, we had this joint work a couple of years ago on the separation between routing and network coding for multiple point-to-point communication problems. All right, so that's more or less my time. Again, I'm David Weitz, and I'm on the faculty job market. Reach out if you have any questions. Enjoy your day.
Perfect. Thanks so much, David. Okay, we're going to swing back to Alex Block, if he's ready. Alex at Purdue.
Do you see my screen?
Yeah, we see your iPad, presumably screen. Yeah, go ahead. We can see your
Okay,
slides
awesome.
as well.
Thank you so much. Sorry about the technical difficulties from earlier. My name is Alex Block. I'm a PhD candidate at Purdue University. My advisor is Jeremiah Blocky. I am hopefully graduating this August, and I'm looking for a postdoc position sometime early August, or late August, early September. So my research mainly is in cryptography and coding theory, and you can break it down into two main themes. So theme one is that coding theory is useful for cryptography, and in my work, I show new ways in which this is true. So for example, coding theory is a key component in an optimal cryptographic object called correlation extractors, and it is implicit in soundness of PCP-based interactive arguments. My second theme is the reverse, which is cryptography is useful for coding theory. So cryptographic analysis techniques can be used to simplify coding theory proofs, and cryptographic models and objects can be used to give new and efficient code constructions. And very briefly, I'm going to talk in a bit more detail about what are my main interests currently. So my first main interest is in space-efficient interactive arguments. So in prior work, what we have done is we construct space-efficient interactive arguments for NP, and then we can do standard techniques to make it non-interactive and zero knowledge. And our key idea was a streaming model, which is that you can generate the transcript of a computation as a stream by just running the computation for a time step and basically encoding its state. So we give constructions under both the discrete log plus random oracle and the unknown order assumptions. And the prover is essentially optimal in terms of time and has some polylogarithmic space overhead. So this is great. And future work in this space, I'm very interested in concrete implementations of the above protocols with performance analysis versus the state-of-the-art ZK snarks now available. Also, concrete security analysis of ZK snarks. This is a very messy area and no one's really tackled it, but I think it would be very interesting. And also applying techniques of the above protocols to construct new interactive arguments under different assumptions, for example, lattices and pairings. My second main interest is in locally decodable codes for insertion deletion errors. This is a more general error model where you can insert and delete symbols from the code word and not just do Hamming errors. So in prior work, we reprove a so-called Hamming to Instel compiler of Ostrowski and Peskin-Taranovsky. And the key idea here was we use cryptographic analysis techniques, which are common to the study of memory hard functions, and create a conceptually simpler and cleaner proof. This compiler basically takes any Hamming locally decodable code and can turn it into a locally decodable code secure against insertion deletion errors, or resilient against that. And then in a follow-up work, we extend this compiler to quote unquote cryptographic codes. What I mean by this is, for example, in the case of private locally decodable codes, the encoder and decoder share a private key. This is a cryptographic assumption. Or when you assume that the channel is resource bounded, for example, the channel can only introduce errors as a PPT algorithm, or it has some space constraints. And future work in this area, I want to be able to know, can we actually construct insertion deletion LDCs without a compiler? As far as I know, there's really no results known like this, and also extend the compiler to other LDCs, for example, relaxed LDCs, computationally relaxed LDCs, other models. And yeah, thank you. That's all I have for today. And again, I'm looking for postdoc late August, early September.
Perfect. Thanks, Alex. If that's it, then we can move on to our final presenter of the session, who is once again Ariel Schwartzman at Dymax. Ariel?
Yep.
Cool.
Okay, I need to give me a second.
Yep. We have a little bit of extra time, so you got some cushion.
There we go. Can you see my screen?
Yeah, we can see your screen. Yep.
Good. Thank you. Thanks everyone for the patience. It seems like there was some Windows update problem.
Classic. All right. Yeah, we can see. Go ahead.
All right. Thank you. So my name is Ariel Schwartzman. I'm an alum from Princeton, and I'm at Dimex now as a postdoc. My work is an approximately optimal mechanism in tournament design, and I'm looking for tenure track positions in theory. So let me tell about the canonical problem in mechanism design. You might have heard of this. Suppose we have a seller on the right, this man with the blue shirt, and there's a woman on the left who wants to buy an apple. She has some private value for the apple. The seller does not know this value, but he knows it comes from some distribution with CDFF. And the question is, how should he price it so as to gain the maximal revenue in the presence of possibly strategic behavior on the part of the buyer? And it turns out that there's a very simple solution for this problem, which is to just post a single posted price given by the formula that I wrote on the slide. This was proven by Meyerson roughly 40 years ago, a contribution for which, among other things, he won a Nobel Prize in economics. And it's a very nice algorithm. It's deterministic, it's simple, it's elegant, it's terrific. And so you might ask, okay, what happens when you're trying to sell more than one fruit, right? So we have apples, bananas, and pineapples. What does the optimal mechanism look like in this case? And the answer is we don't know. After roughly 40 years of research, we know that multi-item optimal mechanisms are complex, they require randomization, they're not intuitive. There's a myriad of lower bounds that make finding optimal mechanisms hard. And my work revolves around circumventing these lower bounds or trying to get around them. So the first way is in the presence of computational hardness results in computer science, what we tend to do is we turn to approximation algorithms. And in our work, we gave the first QP test for a large class of buyers and QP tests for more specific ones. So we give better approximation algorithms. Another way to get around these lower bounds is to study non-heterogeneous items. So part of the reason why it is hard to sell bananas and apples and pineapples is because they're very incomparable. So we study settings where we call them partially ordered or totally ordered items. And we give a p-test for the partially ordered item, and we characterize optimal mechanisms for the totally ordered items. Another way in which we can overcome these impossibility results is going beyond worst case analysis. A lot of the lower bounds for mechanism design arise from very pathological distributions. And so in joint work with co-authors, we initiate the study of smooth analysis for mechanism design, which has been a very celebrated line of work for algorithm design. We're trying to bring it over to mechanism design. And the last and most recent route is to change the benchmark. So in some sense, one of the reasons why optimal mechanisms are so complex is perhaps because we give too much power to the seller. And in recent work, we initiate the study of fine-grained, what we call by many mechanisms. So this was a line of work that started a couple of years ago. And we initiate the study of fine-grained by many mechanisms to prove that a lot of the impossibility results that normally would happen fall apart. So that's my work in mechanism design. You also notice maybe at the start of the slide, I had a word that's a tournament design, which is easier to understand. So, there's a lot of motivation for these questions coming from the Olympics and the World Cup. There's all these sports scandals we hear about every now and then. The most popular one is the women's badminton doubles at the 2012 Olympics in London. It was a cheating scandal. And so a natural question for mechanism designers is to ask if we can design strategy-proof tournaments that will always pick reasonable teams. And Altman and Kleinberg answered this with a no a couple of years ago. And so in our work, which was featured in ITCS a couple of years ago, we asked, can we design approximately strategy-proof tournaments that will always pick reasonable teams? And the answer is yes. Very natural rules actually satisfy strong properties and are optimal in terms of like how much manipulation can happen. And there's lower bounds and connections to other questions in social choice theory. You can ask me about this offline. In an ongoing work, we are trying to understand the effect of teams being selfish. And that is all I have to say. I wanted to thank you for your time and thank again Mark and G for organizing this and part of all of the participants of the session.
Yeah, thanks, Ariel. Thanks for your talk. And again, yes, thank you to all participants for being flexible and willing to jump in when necessary. We had the highest density of talks this entire ITCS, 14 talks within 1 hour. So I'm going to awkwardly give everyone a hand of applause right here by myself. You can give one. All right, Ariel's joining me too. Everyone else can give one on mute at home if you want. But yeah, if you want to see the lineup of speakers again, in case you missed anyone, then check out the website. This session is recorded in case you want to check anyone's talk again. And there's actually going to be another session tomorrow at 9:30 a.m. with a shorter one with only 11 speakers. So please come back for that if you're interested. Thanks a lot, everyone, for joining and participating.
Thank you.
Thanks, Gautam.
Yep.
So much, Gautam.
No problem. Yeah. Everyone was very flexible. I'm impressed. Even with some technical difficulties, people could jump in. So well done, everyone.
Best of luck tomorrow.
Yep. Cool.